Here's something that should terrify you. Right now, an object roughly half a mile wide is racing through our solar system at over 50,000 miles per hour, and what scientists have uncovered after tracing back its path through 10 million years of cosmic history will leave you shocked. Even more disturbing is that the object, the new interstellar visitor 3I Atlas, entered our solar system from almost the same direction as the famous, wow, signal, the one we still can't explain nearly 50 years later. Is it coincidence or choreography? As we peel back the data, we find shocking alignments, anomalies, and possibilities that make even veteran scientists shift uncomfortably in their seats. Keep listening, because tonight we unravel information that changes everything we thought we knew. And if these mysteries keep you awake at night the way they do me, don't just watch from the shadows, step into the investigation, tap like, hit subscribe, and ring the bell so you're here when the next chapter drops. In the comments, tell me where in the world you're tuning in from, what time the clock reads for you right now, and whether you think we're truly getting the full truth about these discoveries, or just the version we're allowed to hear. And if you want to amplify the signal, share this video on X, Facebook, Reddit, or even those midnight group chats. Thank you for standing with us. Part 1. The Origin Search That Found Nothing. Picture this. Astronomers pointed their telescopes backward through time, rewinding the cosmic clock 10 million years into the past. They tracked an object hurtling through our solar system, followed its path through the darkness, and searched for where it came from. What they found was absolutely nothing. Not a single star. Not one credible parent system. Just silence. This isn't a failure of technology or sloppy science. The researchers who conducted this investigation, teams led by Perez Couto and Guo in 2025, used some of the most precise astronomical data ever collected. They tapped into Gaia DR3, a database containing the positions and velocities of over 1 billion stars in our galaxy. They ran simulations backward through time, accounting for gravitational tugs, stellar drift, and the chaotic dance of objects moving through interstellar space. They identified 93 potential stellar encounters, 62 of them statistically significant at the 2 sigma level. They measured every gravitational nudge, every tiny perturbation that could have altered this object's trajectory, and none of it added up. The strongest perturber they found, a distant star that passed relatively close to the object's path about 1.64 million years ago, imparted a velocity change of roughly 5 times 10 to the -4th kilometers per second. That's essentially nothing. To put that in perspective, imagine trying to deflect a speeding bullet by blowing on it. The math simply doesn't work. No star in their analysis could explain how this object gained the tremendous speed it carries today. The object in question is called 3I Atlas, and it's the 3rd confirmed interstellar visitor to our solar system. Its orbit is hyperbolic, meaning it's not bound to our sun. It came from somewhere else, and after its brief visit it will leave forever, disappearing back into the void between stars. Its excess velocity relative to our sun is roughly 58 kilometers per second. That's fast, really fast, the kind of speed that screams I don't belong here. Everything about 3I Atlas confirms it came from beyond our solar system. The trajectory is undeniable, the velocity is clear. Yet when scientists tried to trace it home, they found nothing waiting at the other end. No parent star showed up in the data, no planetary system revealed itself as the obvious source. The backward projection led to empty space, as if the object simply materialized out of the darkness. This isn't supposed to happen. When we detect interstellar objects, we expect to be able to trace them back, at least approximately, to some stellar neighborhood. We might not pinpoint the exact system, but we should see candidates, possibilities, regions of space that make sense as origins. With 3I Atlas, that expectation shattered. The precision of the data made the silence even more disturbing. This wasn't a case of insufficient information. The data were excellent. The models were robust. The answer was simply not there. Some scientists suggested the object might have been ejected from its home system billions of years ago, giving its trajectory time to randomize through countless gravitational interactions. Others wondered if unseen objects, rogue planets, or dark matter structures might have perturbed its path in ways we can't reconstruct. A few even whispered more exotic possibilities, ideas that stretch the boundaries of conventional astrophysics. But here's what makes this truly unsettling. We live in an era where we can measure stellar positions to incredible precision, where we can model gravitational interactions across millions of years, where our computational power lets us rewind cosmic history with startling accuracy. And yet, when we applied all that power to 3i Atlas, the universe offered us nothing but a shrug. The object is real, the data are solid, the origin is missing, and that gap between what we know and what we can't explain opens a door to something far stranger than anyone anticipated. Because if 3i Atlas didn't come from any nearby star, if it didn't originate from any system we can identify, then where did it come from? What kind of cosmic event could eject an object with such speed that its parent becomes invisible in the stellar census? What are we missing? The paradox sits there like a splinter in your mind. An interstellar visitor with no interstellar home. An object moving through space as if dropped from nowhere. And when you start pulling at that thread, when you begin asking what else might be unusual about this visitor, you discover that the missing origin is just the beginning. Because 3i Atlas didn't just arrive from nowhere. It arrived from a very specific direction, one that carries its own strange significance. A direction that points toward one of the most mysterious regions of our entire sky. A place where another famous anomaly once emerged decades ago. The alignment seems too precise to ignore, yet too strange to easily explain. Part 2, Sagittarius alignment. Coincidence or pattern? If you were going to pick a direction in the sky that carries the most cosmic baggage, the most mystery and significance, you'd probably choose Sagittarius. Point your telescope toward that constellation, and you're looking toward the center of our entire galaxy. The supermassive black hole around which hundreds of billions of stars orbit. You're looking toward dense star clusters, regions of intense radiation, zones where the fabric of space-time warps under extreme gravitational forces. Sagittarius isn't just another patch of sky. It's the heart of the Milky Way, and it's been the source of more astronomical puzzles than almost any other region. And now, 3i Atlas comes streaking into our solar system from that exact direction. It's radiant. The point in the sky from which it appears to originate lies in Sagittarius. When astronomers traced the object's trajectory backward, it pointed like an arrow toward that constellation. And here's where things get genuinely weird. Sagittarius is also where the famous WOW signal came from. On August 15th, 1977, the Big Ear radio telescope in Ohio detected a powerful narrowband radio signal that lasted 72 seconds. The signal was so unusual, so distinct from background noise, that the astronomer reviewing the data scribbled "wow" in the margin. It came from the direction of Sagittarius, near the constellation's boundary with other nearby regions. Despite decades of searching, nobody has ever detected it again. Nobody knows what caused it. It remains one of the most tantalizing mysteries in the search for extraterrestrial intelligence. Now, we have an interstellar object arriving from the same general region of the sky. Some researchers, notably Avi Loeb, calculated the probability of this alignment. According to his analysis, the chance of 3i Atlas's trajectory randomly matching the WOW signal's direction to within about 9 degrees is roughly 0.6%. That's not impossible, but it's uncomfortably low. It's the kind of number that makes you pause and wonder if you're witnessing coincidence or something more structured. Could Sagittarius act as some kind of cosmic hub, a gravitational crossroads where objects naturally congregate or get funneled outward? The galactic center exerts enormous gravitational influence on everything in its vicinity. Stars orbit faster there. Tidal forces are extreme, and the density of matter creates a chaotic environment where interactions happen frequently. Perhaps that chaos acts as a kind of scattering center, flinging objects outward in all directions, and we're simply seeing one that happened to reach us. Some theorists propose that the galactic center could generate streams of debris through tidal disruption events, where stars or planetary systems get torn apart by gravitational forces and their remnants scattered across the galaxy. Others suggest that resonance patterns in galactic orbits might create preferred pathways, channels through which interstellar material flows more readily. These aren't mainstream ideas, but they're not completely fringe either. They represent attempts to make sense of a pattern that seems too specific to dismiss. Skeptics, however, point out that Sagittarius covers a large area of sky. It's not a pinpoint. When you say something comes from Sagittarius, you're describing a broad region, not an exact location. The constellation spans roughly 30 degrees of celestial longitude. That's a huge swath of the galaxy. Finding an alignment within that region might feel meaningful, but statistically it's less impressive than it first appears. Critics also note that we're engaging in what's called post hoc reasoning, looking at where 3i Atlas came from after we already know about the wow signal, and then marvelling at the connection. If the object had come from any other direction, we'd probably find some other anomaly to link it with. Yet the alignment persists as a nagging detail, something that refuses to disappear under scrutiny. Even if it's coincidence, it's the kind of coincidence that makes you wonder what else you might be missing. Because direction isn't the only unusual thing about 3i Atlas. Its velocity tells a story too, one that's equally confusing and contradictory. When astronomers analysed the object's motion through space, they broke down its velocity into galactocentric components, measurements relative to the centre of our galaxy rather than our Sun. The numbers came out to roughly negative 51.2 km per second in the U direction, negative 19.5 in V, and positive 18.9 in W. Those might seem like arbitrary figures, but they tell us something crucial. 3i Atlas moves like an object from our galaxy's thin disk. The thin disk is where most ordinary stars live, including our Sun. It's the pancake-shaped region of younger stars, gas and dust that defines the visible spiral structure of the Milky Way. Objects in the thin disk share similar velocities because they all orbit the galactic centre in roughly the same plane. When you measure 3i Atlas's kinematics, it fits that profile. It's moving like it belongs to the same population as local stars. But here's the paradox. If it's moving like a thin disk object, why can't we find its parent in the thin disk? Why does its backward trajectory lead nowhere? It's like discovering a car moving at highway speed, but finding no highway that leads to it. The motion suggests local origin, but the origin itself has vanished. And that contradiction drives us toward a deeper mystery, one that forces us to question not just where 3i Atlas came from, but what it actually is. Part 3. The Speed Problem and Thin Disk Puzzle. Speed in space isn't like speed on Earth. When something moves fast through our solar system, that velocity tells a story about where it came from and what happened to it along the way. 3i Atlas carries an excess hyperbolic speed of approximately 58 km per second relative to our Sun. That's roughly 200,000 km per hour, fast enough to escape the Sun's gravity and wander the galaxy forever. Objects in our solar system don't naturally reach those speeds unless something dramatic happened. Comets can slingshot around planets and pick up velocity, but 58 km per second is beyond what local gravitational assist can easily explain. That speed marks 3i Atlas as foreign, as something that doesn't originate from our neighbourhood. Yet when astronomers examined how that speed breaks down into components, they discovered something puzzling. Galactocentric velocity components measure how an object moves relative to the galaxy's centre of mass. The U component describes motion toward or away from the galactic centre. The V component describes motion in the direction of galactic rotation. The W component describes motion perpendicular to the galactic plane, either up or down. For 3i Atlas, these values are approximately negative 51.2, negative 19.5, and positive 18.9 km per second respectively. Those numbers place 3i Atlas squarely within the kinematic range of thin disk stars. The thin disk population consists of relatively young stars, typically less than a few billion years old, orbiting the galaxy in a flattened distribution. Most stars visible to the naked eye belong to this population. Their velocities cluster around predictable values because they formed from the same rotating cloud of gas and share similar orbital characteristics. 3i Atlas fits that pattern. Its motion suggests it's a member of the thin disk community. But that makes no sense given what we know about its origin, or rather, what we don't know. If 3i Atlas moves like a thin disk object, it should trace back to a thin disk star. The backward integration should reveal a parent system somewhere in our local stellar neighbourhood. Yet, it doesn't. The traceback leads nowhere. It's as if the object belongs to a population it can't possibly belong to. Researchers working on this problem, including Hopkins and collaborators, compared 3i Atlas's kinematics to a large sample of stars in Gaia DR3. They looked for kinematic analogues, stars that share similar velocity distributions, to understand which stellar populations the object most resembles. The comparison confirmed the thin disk association. 3I Atlas doesn't move like a high-velocity halo object or a thick disk wanderer. It moves like something that formed locally, recently, and should be traceable to a nearby system. One possible explanation involves ancient ejection. Maybe 3I Atlas was kicked out of its home system billions of years ago, long before Gaia's stellar sensors could track it. Over billions of years, gravitational interactions with passing stars, molecular clouds, and other massive objects would gradually randomize its trajectory. Even if it started with clear kinematic signatures pointing to a specific origin, those signatures could erode over time. The object would retain velocity components that superficially matched the local population, but its actual birthplace would be lost to the chaos of cosmic history. Another possibility involves unseen perturbers. Our galaxy contains objects we can't easily detect. Rogue planets drifting without parent stars, black holes wandering through interstellar space, massive molecular clouds that occasionally pass close to stellar systems. Any of these could gravitationally deflect 3I Atlas in ways that wouldn't show up in Gaia data because Gaia only catalogues luminous stars. If the object's trajectory was significantly altered by an invisible perturber within the last few million years, our backward integration would miss the encounter entirely. Some researchers also point out that Gaia DR3, while extraordinary, isn't complete. Faint stars, especially dim red dwarfs, might not have reliable radial velocity measurements in the catalogue. If 3I Atlas originated from a particularly faint or distant system, that system might exist in Gaia's data but lack the precise measurements needed for accurate traceback. The silence might not mean no parent exists, just that we can't identify it yet. But those explanations feel unsatisfying. They're logical, reasonable, and scientifically defensible, yet they don't quite capture the strangeness of the situation. We're not just missing one piece of information, we're missing the entire puzzle, and as you sit with that mystery, you start wondering if maybe the physical characteristics of 3I Atlas itself might offer clues. Maybe the object's appearance, its composition, its behaviour as it moves through our solar system could tell us something about where it came from or what it is. So let's look at what we actually see when we observe 3I Atlas, because what astronomers have found is almost as strange as the missing origin. Part 4. Observations on the table. What 3I Atlas actually looks like. On July 1st, 2025, the Atlas telescope system in Chile detected something unusual. A moving object appeared in the sky, too fast and on the wrong trajectory to belong to our solar system. Within days, astronomers confirmed it was interstellar, the third such visitor we've identified. They named it 3I Atlas and immediately began gathering every possible observation before it disappeared forever. The object was detected at roughly 4.5 astronomical units from the Sun, inbound on its hyperbolic trajectory. An astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. So 3I Atlas was still fairly distant when we first spotted it. But here's something interesting. Pre-discovery imaging revealed the object had been visible earlier. The Zwicky Transient Facility, a survey telescope that scans the sky for changing objects, had captured images of 3I Atlas as far out as 6.5 astronomical units, weeks before its official discovery. Those early images showed something unexpected. 3I Atlas was active. It wasn't just a cold rock drifting through space. It displayed a visible coma, a cloud of dust and gas surrounding the nucleus, and it was brightening as it approached the Sun. The brightness followed a steep power law, roughly proportional to heliocentric distance to the negative 3.8 power. That's steeper than 2I/Borisov, the previous interstellar comet, which followed a more typical brightening curve. The steep slope suggests 3I Atlas was producing dust at an unusually high rate as it warmed up. When the Hubble Space Telescope turned its gaze toward 3I Atlas, astronomers got their first detailed look at the coma structure. They observed a dust tail extending away from the Sun, driven by radiation pressure, and they estimated mass loss rates between 6 and 60 kilograms per second, depending on assumptions about particle size. That might not sound like much, but over weeks and months it adds up to millions of kilograms of material streaming off the nucleus. The object was actively sublimating, turning ice directly into gas without melting, exactly as comets do. Spectroscopic observations provided more details. Visible light spectra showed the object was slightly red, with a spectral slope of approximately 18.3% per thousand angstroms. That coloration is similar to what we see in D-type asteroids, trans-Neptunian objects, and centaurs, bodies found in the outer solar system rich in organic compounds and dark, carbon-rich material. The redness suggests 3I Atlas's surface is covered in processed, irradiated ices and rocky material that's been weathered by cosmic rays over possibly billions of years. Light curves, measurements of how the object's brightness changes over time, revealed a rotation period of approximately 16.79 hours. That's a reasonably normal rotation rate for a comet-sized body, neither unusually fast nor remarkably slow. The rotation introduces periodic variations in brightness, likely due to the nucleus's irregular shape or uneven surface reflectivity. Astronomers use these variations to infer the object's approximate dimensions and rotational state. But one of the most unusual observations came from polarimetry, measurements of how light scatters off the object's coma and nucleus. Polarimetry can reveal details about particle size, composition, and surface structure. 3I Atlas displayed an extreme negative polarization branch, reaching a minimum of roughly negative 2.7% and an unusually narrow inversion angle around 17 degrees. That's unlike typical comets or asteroids. The polarization signature suggests something different about the dust particles, perhaps their size distribution or their composition, that doesn't match standard cometary models. Estimating the nucleus size has proven tricky because the dust coma outshines the solid nucleus. Early images from the Vera Rubin Observatory suggested a diameter around 11 kilometers, roughly 7 miles across, making 3I Atlas comparable in size to some of our solar system's larger comets. But that estimate carries significant uncertainty. We're essentially trying to measure a small dark object hidden inside a bright cloud of dust. Then there are the more controversial claims. Some reports, particularly from Avi Loeb's team, suggest that 3I Atlas shows unusual compositional signatures. Specifically, they claim the object's gas is dominated by carbon dioxide rather than water vapor, and that spectroscopic analysis hints at nickel-rich material in the plume. These claims haven't been fully peer-reviewed or confirmed by other teams, so they remain speculative. If true, they'd suggest a very different formation environment than typical comets, which are usually water ice dominated. None of these physical characteristics individually screams alien artifact. Comets come in many varieties. Interstellar comets could be even more diverse, formed in environments vastly different from our own solar system. But taken together, the observations paint a picture of something unusual. Not impossible, not physics-defying, just odd. The steep, brightening curve, the extreme polarization, the tentative compositional anomalies, they all nudge 3I Atlas slightly outside the comfortable box of normal interstellar comet. And that oddness compounds the central mystery. We have this strange object, moving like a thin disk member, arriving from Sagittarius, displaying unusual physical properties, and we have no idea where it came from. The silence surrounding its origin isn't just an empty void. It's a pressure point where speculation begins to seep in, where the gap between what we know and what we don't pushes us toward uncomfortable questions. Because when you can't find the origin, you start wondering if maybe the origin is something we haven't considered. Part 5. The silence between the stars. Why no origin is shocking. There's a particular kind of unease that comes from missing information. Not speculation, not wild theories, just the simple absence of an answer where an answer should exist. 3I Atlas presents us with exactly that kind of void. We have the object, we have its trajectory, we have precise measurements of its position and velocity. We have sophisticated models that can trace orbital paths backward through millions of years. We have a catalogue containing over 1 billion stars with known positions and motions. And yet, when we combine all of that, we find nothing. Let's appreciate how unusual that is. When we detected Oumuamua in 2017, the first confirmed interstellar object, astronomers quickly identified several plausible source regions. The trajectory pointed vaguely toward the Lyra constellation and the Vega star system. While we couldn't definitively say it came from Vega, we had candidates, possibilities that made sense given the kinematics. Oumuamua's origin wasn't certain, but it wasn't silent either. When 2I/Borisov arrived in 2019, the story was even clearer. Its trajectory suggested ejection from a planetary system, and its behavior matched expectations for a comet from another star. Borisov looked and acted exactly like we'd expect an interstellar comet to look and act. Its origin might be unknown, but its nature was familiar. We understood what we were seeing, even if we couldn't name its parent star. 3I/Atlas breaks that pattern. It's not that we have weak candidates or uncertain matches, it's that we have no credible candidates at all. The best match in Perez-Couto's analysis was a wide M-dwarf binary system that passed within roughly 0.242 parsecs, about 79 trillion kilometers, moving at approximately 28 kilometers per second, around 1.64 million years ago. That flyby imparted essentially negligible velocity change, nowhere near enough to explain 3I/Atlas's current speed. Go's analysis, using similar methods but slightly different assumptions, reached the same conclusion. 93 stellar encounters identified, 62 statistically significant, and none strong enough to be the ejection source. The encounters were too distant, too brief, or involved stars too low in mass to gravitationally accelerate 3I/Atlas to its observed velocity. The data don't show a failed detection or a borderline candidate. They show a clean miss. This challenges fundamental assumptions about how interstellar objects get ejected from planetary systems. The standard model involves gravitational interactions during planetary system formation. Young planets migrate, their orbits shift, and in the process they fling countless small bodies, comets, asteroids, planetesimals outward at high speeds. Some of those ejected objects escape their home system entirely and wander into interstellar space. Over billions of years, the galaxy accumulates a population of these wanderers, and occasionally one passes through our solar system. That model works well for objects like Borisov. But 3I/Atlas seems to violate the model's predictions. If it was ejected from a nearby star system through normal planetary interactions, we should see that system in Gaia's catalogue. If it was ejected from a more distant system millions or billions of years ago, its kinematics should show signs of that ancient origin through randomized velocity components that don't match local populations. Neither is true. 3I/Atlas looks local, but has no local origin. One possibility is that the object is genuinely ancient, ejected billions of years ago when our galaxy looked very different. Back then, star formation rates were higher, stellar encounters were more frequent, and the gravitational environment was more chaotic. An object ejected in that era would have experienced countless weak perturbations over billions of years, each nudge slightly altering its trajectory until the original ejection event became impossible to reconstruct. It would wander the galaxy like a ghost, its past erased by the cumulative chaos of gravitational interactions. Another possibility involves unseen or unmodelled objects. Gaia catalogues stars, but our galaxy contains much more than stars. Rogue planets, brown dwarfs, stellar remnants, molecular clouds, all of these could perturb an object's trajectory without showing up in stellar catalogues. If 3I/Atlas encountered a massive rogue planet or passed through a dense molecular cloud within the last few million years, that interaction could deflect it significantly. Our models would miss the encounter because they only account for catalogued stars. Some researchers point to Gaia's limitations. While the catalogue is extraordinary, it's not complete. Faint red dwarfs in the outer halo might lack accurate measurements. Stars obscured by dust clouds might be missing or have uncertain positions. If 3I/Atlas came from a particularly faint or distant system, one right at the edge of Gaia's detection threshold, the data might simply not be good enough to identify it. The silence could be an artifact of incomplete information, rather than a true absence. But there's another class of explanations, one that strays further from conventional astrophysics. What if 3I/Atlas didn't originate from a single star system at all? What if it was ejected from a stellar cluster that subsequently dissolved? Open clusters, loose associations of stars that form together but gradually drift apart, become unrecognizable over time. If 3I/Atlas came from such a cluster billions of years ago, the cluster would now be dispersed across a wide region of the galaxy, its members indistinguishable from background stars. We'd never identify them as a coherent group. Or what if the parent system no longer exists? Stars can be disrupted by close encounters with black holes. Small stellar systems can be torn apart by tidal forces near the galactic center. If 3I Atlas's parent star was destroyed or gravitationally stripped after ejecting the object, there'd be nothing left to trace back to. The origin would be genuinely absent, not because we can't find it, but because it's gone. These explanations venture into uncomfortable territory where the simple mechanical model of ejection and traceback starts to fray. And that's where the real speculation begins, the point where some researchers start asking whether 3I Atlas might not be a natural object at all, whether it might be something designed, something sent, something that defies natural explanations because it wasn't created through natural processes. That idea seems absurd until you remember that we're already facing an absurd situation, an interstellar object with no traceable origin, despite having all the tools to find one. And once you admit that the situation is absurd, other absurdities start seeming less impossible. Part 6. The Sagittarius Hypothesis. Is it a galactic hub? Sagittarius isn't just a constellation. It's a window into the most gravitationally extreme region of our galaxy. When you look towards Sagittarius, you're looking towards Sagittarius A star, the supermassive black hole at the galactic center, weighing roughly 4 million times the mass of our Sun. You're looking at dense star clusters where stellar encounters happen frequently, where gravitational interactions routinely tear systems apart and fling debris across vast distances. You're looking at a region bathed in intense radiation, both from the black hole's accretion disk and from millions of nearby stars. Could that environment act as a kind of cosmic launcher, a gravitational hub that preferentially sends objects outward in certain directions? The idea seems plausible at first glance. The galactic center's enormous mass creates steep gravitational gradients. Objects passing too close experience extreme tidal forces strong enough to disrupt planets, shred comets, and accelerate fragments to high velocities. If 3I Atlas originated in that environment, its unusual speed might be explained by a close encounter with the central black hole or a hyperbolic flyby through a dense star cluster. The concept of gravitational focusing has precedent in astrophysics. When objects orbit in a massive gravitational field, certain trajectories get preferentially amplified or redirected. In our solar system, gravitational focusing by Jupiter affects the distribution of comets and asteroids. On a galactic scale, the central black hole and surrounding stellar mass could create similar focusing effects, channeling objects along preferred pathways. Those pathways wouldn't be visible, they're not physical structures, but they'd show up statistically in the distribution of trajectories for objects originating near the galactic center. Some researchers propose that the galactic center generates streams of debris through tidal disruption events. When a star or planetary system passes too close to Sagittarius A star, tidal forces stretch and compress the object until it breaks apart. The debris forms a stream of fragments, each piece following a slightly different orbit. Over time, those streams disperse, and individual fragments wander outward into the galaxy. 3I Atlas could be a fragment from such an event, ejected millions of years ago and now arriving at our solar system. There's also the possibility of resonance structures. Galactic orbits aren't random. They follow patterns determined by the overall mass distribution of the galaxy. Certain orbital configurations repeat, creating resonance zones where objects tend to accumulate or get channeled. These resonances might create preferred directions for ejection, pathways along which debris naturally flows. If Sagittarius lies along one of these pathways, we might expect to see more interstellar objects arriving from that direction, simply because that's where the gravitational channels point. But there are problems with the Sagittarius hub hypothesis. First, Sagittarius is big. The constellation covers a substantial fraction of the sky. Saying 3I Atlas comes from Sagittarius is like saying someone comes from North America. It's a region, not a pinpoint, and the statistical significance of an alignment depends heavily on how precisely you define the target area. If you allow too much wiggle room, any direction can be made to seem significant. Second, the galactic center is far away, roughly 27,000 light-years from Earth. For 3I Atlas to have originated there and still display thin disk kinematics, its trajectory would need to have been remarkably stable over that entire journey. Gravitational perturbations from passing stars and spiral arm crossings should randomize the velocity components over such distances. The fact that 3I Atlas looks kinematically local argues against a distant origin. Third, tidal forces near the galactic center are brutal. Objects don't gently get accelerated and sent on their way. They get shredded, vaporized, and scattered into clouds of debris. Surviving such an environment intact as a coherent comet-sized body seems difficult. Most objects passing through the galactic center's tidal radius would be destroyed, not launched. Critics also point out that we've now seen 3 interstellar objects in less than a decade, and only one of them arrives from Sagittarius. Oumuamua came from the direction of Lyra. 2I/Borisov came from roughly the direction of Cassiopeia. If Sagittarius were a special ejection zone, we'd expect more arrivals from that direction, not just 1 out of 3. The small sample size makes any pattern suspect. Yet the alignment with the WOW signal remains tantalizing. That signal, detected 48 years ago, was a narrowband radio pulse at precisely the frequency hydrogen atoms emit when their electrons flip spin states. It's the kind of signal that intelligent civilizations might use for interstellar communication because it's a universal frequency, one that any technologically advanced species would recognize. The signal lasted 72 seconds, then never repeated. It came from Sagittarius, and now an interstellar object arrives from the same region. You could dismiss that as coincidence. Space is full of anomalies. Radio telescopes detect transient signals constantly, most of which turn out to be terrestrial interference or natural astrophysical phenomena. Interstellar objects arrive from random directions. Finding a directional match between 2 unrelated events isn't that surprising when you consider how many events we've observed over the decades. But coincidences make people uncomfortable, especially when they involve 2 of the strangest phenomena ever detected. And discomfort breeds speculation, which brings us to the next uncomfortable thought. If Sagittarius is special, maybe it's special for reasons beyond simple gravitational mechanics. Part 7. The Radio Bubble and Cosmic Eavesdropping. For roughly 100 years, humanity has been leaking radio signals into space. It started with early radio transmissions in the 1920s, grew with television broadcasts in mid-century, and exploded with radar installations, satellite communications, and now billions of wireless devices. All of that electromagnetic radiation doesn't just stay on Earth. It propagates outward at the speed of light, spreading in an expanding sphere around our planet. That sphere, our radio bubble, now extends approximately 100 light-years in radius. Within that bubble, any civilization with sufficiently sensitive receivers could detect us. They'd pick up scattered signals, fragments of broadcasts, maybe even coherent transmissions if they knew where to look and how to filter out the noise. They wouldn't necessarily understand what they were hearing. Human languages and protocols would be utterly alien, but they'd know something was generating organized electromagnetic emissions. They'd know we exist. Now ask yourself this: how many star systems lie within 100 light-years of Earth? The answer is roughly 14,000. That includes stars of all types, from massive blue giants to tiny red dwarfs. Many of those stars likely host planets. Some of those planets might be habitable. And if even a tiny fraction harbour intelligent civilizations, then potentially dozens or even hundreds of them could already be aware of us. Sagittarius lies in the general direction of the galactic centre, much farther than 100 light-years away. But the direction matters. If a civilization existed somewhere along the line of sight towards Sagittarius, even at a considerable distance, and if they had sufficiently advanced technology, they might detect our radio bubble, and if they detected it, they might respond. Not with radio signals, which would take decades or centuries to arrive, but with something faster, something physical, something that could arrive within a reasonable time frame and gather data directly. This is pure speculation, but it's not scientifically illiterate speculation. The physics allows it. If you wanted to investigate a newly detected technological civilization, sending a physical probe makes sense. Radio communication is slow and ambiguous. You can't control what messages you receive, and the round-trip time for dialogue spans decades or centuries. A probe, on the other hand, could arrive, observe, collect samples if needed, and either report back or move on to the next target. 3I/Atlas could, in principle, be such a probe. Its trajectory brought it into our solar system during an era when we've become radio loud. Its arrival coincides with our technological adolescence. If it were designed for reconnaissance, You'd expect it to look mostly natural to avoid drawing attention. You'd camouflage it as a comet or asteroid, something we'd catalogue and observe but not immediately recognise as artificial. You might even design it to sublimate and produce a dust coma, mimicking natural outgassing to hide any internal structure. But before we get carried away, let's establish what evidence would actually support that hypothesis. If 3I Atlas were artificial, we'd expect to see certain signatures. First, trajectory anomalies. Natural objects follow predictable orbits determined by gravity and, in the case of comets, outgassing forces. An artificial object might maneuver, changing its trajectory in ways that don't match outgassing models. So far, 3I Atlas hasn't shown such anomalies, but observations are ongoing. Second, we'd look for non-gravitational accelerations that can't be explained by sublimation. Comets experience tiny pushes when gas jets away from their surfaces, creating rocket-like forces. These forces are measurable and follow predictable patterns based on the comet's rotation and sun exposure. An artificial object might show accelerations that don't match those patterns, suggesting propulsion rather than natural outgassing. Again, no clear evidence exists yet, but the data are still being analysed. Third, we'd search for anomalous electromagnetic emissions. A functioning probe might emit radio signals, either for communication or as a byproduct of internal systems. Radio telescopes have been pointed at 3I Atlas, particularly by teams associated with the Breakthrough Listen project, searching for exactly such signals. So far, they've detected nothing unusual. The object is radio quiet, at least at the sensitivities and frequencies searched. Fourth, we'd look for structural anomalies in high-resolution imaging. If the nucleus isn't a natural rock but rather a constructed object, sufficiently powerful telescopes might detect geometric regularities, surface features that suggest manufacturing rather than natural formation. The problem is that 3I Atlas's dust coma obscures the nucleus. We can't see the solid surface clearly enough to identify such features, assuming they exist. The burden of proof for artificial origin is extraordinarily high, as it should be. Extraordinary claims require extraordinary evidence. Carl Sagan's principle remains valid. You can't invoke aliens to explain something without first exhausting all natural explanations, and natural explanations for 3I Atlas, while incomplete and unsatisfying, do exist. It could be an ancient ejection, it could be from a disrupted cluster, it could be from a system we simply can't identify yet due to data limitations. Yet the speculation persists, because the missing origin creates a vacuum that speculation rushes to fill. Avi Loeb and collaborators published a paper in 2025 titled "Is the Interstellar Object 3I Atlas Alien Technology?", exploring exactly this possibility. The paper isn't a claim of discovery, it's an investigation of what signatures we should look for and what anomalies might suggest artificial origin. It's provocative, controversial, and many scientists criticize it as premature. But it serves a purpose. It forces us to think about what evidence would actually convince us and what we should be watching for as observations continue. The eavesdropping hypothesis ties into a broader question about interstellar civilizations and how they might operate. If technological species exist in our galaxy, they're probably not all at the same level of development. Some might be far more advanced than us, capable of interstellar travel or at least interstellar object deployment. Those civilizations would face the same challenge we do, detecting other technological species across vast distances. Radio signals are one method, but they're slow and ambiguous. Physical probes offer direct data collection and could be scattered throughout the galaxy as a kind of monitoring network. Imagine a civilization that, millions of years ago, deployed thousands or millions of probes into the galaxy, seeding them along likely trajectories to encounter planetary systems. Most probes would find nothing, just barren rocks and lifeless gas giants. But occasionally one might encounter a world with biological activity or even technology. When that happens, the probe could activate, observe, and report back. From the probe's perspective, even if its parent civilization no longer exists, the mission continues. 3. I/Atlas's arrival from Sagittarius might then be less about Sagittarius being special and more about the distribution of probe trajectories. If an ancient civilization deployed monitoring systems throughout the galaxy, some of those systems would naturally arrive from the direction of the galactic center simply because that's where a significant fraction of the galaxy's mass and stars are concentrated. The alignment wouldn't be meaningful in terms of the probe's origin, but rather in terms of the galactic distribution of monitoring assets. This is all speculation built on speculation, layers of hypothesis without solid evidence. But the exercise reveals something important. When you can't explain an object's origin through conventional means, your mind starts exploring unconventional possibilities. And once you start down that path, you notice other patterns, other anomalies that might be related. Which brings us to an uncomfortable realization. 3i Atlas isn't the only strange visitor we've seen recently. Part 8. Lost clusters and phantom parents. Stars don't always live alone. Many form in groups, born together from the same collapsing cloud of gas and dust. These stellar nurseries produce clusters ranging from small associations of a few dozen stars to massive open clusters containing thousands of members. For a few million years, these clusters remain coherent, their member stars orbiting a common center of mass and moving through space together. But gravity is both creative and destructive. Over time, encounters with other clusters, tidal forces from the galaxy, and internal dynamics cause clusters to dissolve. Stars drift apart, their orbits randomize, and eventually the cluster disappears as a recognizable structure. This process of cluster dissolution might explain why we can't find 3i Atlas's parent. If the object was ejected from a young planetary system within a star cluster billions of years ago, that cluster would now be completely dispersed. Its member stars would be scattered across a huge volume of space, indistinguishable from the background stellar population. Even if we could identify some of the former cluster members in Gaia's catalogue, we'd have no way to reconstruct the cluster's original configuration or determine which star ejected 3i Atlas. The idea isn't without precedent. Our Sun almost certainly formed in a cluster. The early solar system contained more stars than just our Sun, dozens or hundreds of siblings born from the same molecular cloud. Those siblings are now scattered throughout the galaxy, too distant and dispersed to identify as related to our Sun. If we were trying to trace an object ejected from the early solar system, we'd face the same challenge. The parent cluster has vanished into the stellar background. 3i/Atlas's thin disk kinematics actually support the cluster hypothesis. Objects ejected from clusters early in the galaxy's history would, over time, mix into the general disk population. Their velocities would gradually adjust to match local stars through countless weak gravitational interactions. By the time such an object reached our solar system, it would display kinematics consistent with the thin disk, despite having originated from a specific cluster billions of years ago. But there's a timing problem. Clusters dissolve relatively quickly on galactic timescales, typically within a few 100 million years. If 3i Atlas was ejected from a cluster, it would need to have been wandering the galaxy for a very long time to ensure the cluster completely dissolved. That long wandering time increases the probability of major gravitational perturbations that would randomize its trajectory beyond recognition. The fact that we can trace its path back 10 million years with confidence suggests its trajectory hasn't been drastically altered recently, which argues against an ancient, highly perturbed origin. Another complication involves ejection mechanisms. Clusters are gravitationally active environments. Young planets interact with each other and with passing stars, creating opportunities for high-velocity ejections. But most ejections from clusters wouldn't reach the speeds 3i Atlas displays. Typical ejection velocities from planetary scattering events are a few kilometers per second relative to the parent star. To reach 58 kilometers per second, excess velocity requires something more violent, like a close stellar flyby during planetary system formation, or a multi-body interaction involving several massive objects simultaneously. Some researchers propose that 3i Atlas might have been ejected during a binary star encounter. Binary star systems, where two stars orbit each other, are common in clusters. If a planetary system orbits one member of a binary, and that binary encounters another binary or a passing star, the resulting gravitational chaos can fling planets and smaller bodies outward at very high speeds. Such interactions are rare, but in a large cluster over millions of years they happen. 3i Atlas could be a survivor of such an encounter, accelerated to high velocity and sent wandering while its parent cluster gradually dissolved. There's also the possibility of dark perturbers, objects that don't shine but still exert gravitational influence. Rogue planets are common in the galaxy, possibly more numerous than stars. Brown dwarfs, objects too massive to be planets, but too small to sustain hydrogen fusion, lurk in vast numbers throughout interstellar space. Stellar remnants like white dwarfs, neutron stars, and black holes wander as well. None of these objects would show up in Gaia's optical catalogue unless they happen to have a luminous companion. If 3i Atlas encountered a massive rogue planet or brown dwarf within the last few million years, that encounter could significantly deflect its trajectory without leaving any trace in stellar catalogues. Our backward integration would show a gap, a discontinuity in the traceable path, exactly what we observe. The phantom parent wouldn't be a star at all, but rather an invisible gravitational scatterer that pushed 3i Atlas onto its current trajectory. Go and collaborators identified the strongest candidate encounter as a wide M-dwarf binary system, passing within roughly 0.242 parsecs at a relative velocity of about 28 kilometers per second, around 1.64 million years ago. That encounter was too distant and too fast to impart significant velocity change. But what if there were another closer encounter with an object we can't see? What if a rogue planet passed within, say 0.01 parsecs, close enough to gravitationally deflect 3i Atlas substantially? Such an encounter wouldn't appear in the stellar catalogue, and we'd never know it happened. The challenge with invoking unseen perturbers is that it becomes an unfalsifiable hypothesis. You can always propose that something we can't detect explains what we can't explain. It's scientifically unsatisfying because it doesn't predict anything testable. We can't search for the perturber because we don't know where to look or what to look for. The hypothesis merely shifts the mystery from we can't find the parent star to the parent was something else we also can't find. Yet another speculative possibility involves the parent system's destruction. Stars can be disrupted by close encounters with black holes, particularly near the galactic center. If 3i Atlas originated from a star that subsequently passed too close to Sagittarius A star, the star could have been tidally shredded, leaving no intact parent to trace back to. The timing would be tricky. The ejection would need to have happened before the disruption, and the star would need to have survived long enough after ejecting 3i Atlas for the object to travel to our solar system. Black hole disruptions aren't gentle. When a star passes within the tidal radius of a supermassive black hole, gravitational gradients stretch it into a long stream of plasma. Most of the stellar material either falls into the black hole or gets ejected at high velocity. Planetary systems orbiting the star would be torn apart as well, their planets scattered or destroyed. 3i Atlas would need to have been ejected before the disruption occurred, then the parent star subsequently destroyed, erasing any possibility of tracing the object's origin. These explanations share a common theme. They all propose that 3i Atlas's parent is gone, disguised, or invisible. The cluster dissolved. The star was destroyed. The perturber is dark. Each hypothesis rescues the natural ejection model by invoking something we can't directly observe. And while that's scientifically legitimate, it's also unsatisfying. We're left with an object whose origin is lost not because we lack technology or data, but because the universe has conspired to hide the answer. That feels like a narrative, like a story the cosmos is telling, and we're only hearing fragments. Part 9. Controversial. Takes artificial object hypothesis. Let's be clear from the start. Proposing that an interstellar object might be artificial is scientific dynamite. It invites ridicule, skepticism, and accusations of sensationalism. Carl Sagan's warning echoes through the decades. Extraordinary claims require extraordinary evidence. Suggesting that 3i Atlas could be a probe, a manufactured artifact rather than a natural comet, sits firmly in the extraordinary claim category. So why are some scientists willing to explore this possibility despite the risks? The answer lies in precedent. When Oumuamua arrived in 2017, its unusual shape inferred from light curves suggested an elongated object, possibly 10 times longer than it was wide. Its trajectory showed slight non-gravitational acceleration that couldn't easily be explained by outgassing because no coma was detected. Those anomalies prompted Avi Loeb and Shmuel Bialy to publish a paper exploring whether Oumuamua could be a light sail, a thin reflective structure pushed by radiation pressure. The idea was wildly controversial. Many scientists criticized it as premature speculation. but it also forced the community to articulate what evidence would actually support artificial origin and what observations could rule it out. With 3i Atlas, Loeb and collaborators have published another exploratory paper. Is the interstellar object 3i Atlas alien technology? The paper doesn't claim 3i Atlas is artificial. Instead, it examines what signatures might indicate artificiality and whether any observed features of 3i Atlas match those signatures. The approach is methodical: define criteria, check observations, assess probabilities. One claimed anomaly involves the object's trajectory. 3i Atlas's orbit brought it unusually close to the ecliptic plane, the plane in which Earth and most planets orbit the Sun. Some researchers note that if you were designing a probe to survey planetary systems, you'd want it to pass through the ecliptic to maximize encounters with planets. A natural interstellar object arriving from a random direction should have a random inclination, not preferentially aligned with our planetary system's architecture. But here's the problem with that argument. We have a selection bias. We detect interstellar objects more easily when they pass close to Earth. Objects that pass through the ecliptic are more likely to come near Earth than objects with high inclinations. So finding an interstellar object near the ecliptic might not indicate artificial design. It might simply reflect our detection bias. We wouldn't see the ones with high inclinations as easily. Another claimed anomaly involves spectroscopy. Loeb's team suggests that 3i Atlas doesn't show the expected spectral lines for water ice sublimation. Instead, they claim carbon dioxide dominates the gas emission, with hints of nickel-rich material in the dust. If confirmed, this would be unusual. Most comets are water-dominated because water ice is abundant in planet-forming regions. A carbon dioxide-dominated object might suggest formation in a very cold environment, far from any star, where water froze out but carbon dioxide remained volatile. However, these spectroscopic claims haven't been peer-reviewed or independently confirmed. Other teams analysing 3i Atlas haven't reported the same findings. Spectroscopy is tricky, especially for faint, fast-moving objects surrounded by dust. Contamination, calibration errors, and signal-to-noise issues can produce misleading results. Until other teams replicate the findings, they remain tentative. A third claimed anomaly involves size. Early estimates suggested 3i Atlas might have a nucleus roughly 11 kilometers in diameter. That's large for an interstellar comet. Larger objects are rarer because fragmentation and collisional erosion tend to break down big bodies over time. An 11-kilometer object surviving intact through interstellar space for millions or billions of years without significant erosion would be somewhat unusual, though not impossible. But again, the size estimate is uncertain. The dust coma obscures the nucleus, making direct measurement difficult. Different methods produce different estimates. Some analyses suggest a smaller nucleus, a few kilometers across, which would be more typical. Without high-resolution imaging that pierces through the coma, we can't definitively measure the nucleus size. The artificial object hypothesis also predicts certain observable signatures. If 3i Atlas were a probe, it might maneuver. Active propulsion would create trajectory anomalies inconsistent with gravitational forces and outgassing. So far, no such anomalies have been detected, but observations continue. The object is still being tracked, and if it changes course in a way that can't be explained naturally, that would be significant. An artificial object might also emit electromagnetic radiation. Internal systems, power sources, communication devices, any of these could produce detectable signals. Breakthrough Listen, a project dedicated to searching for signs of extraterrestrial technology, has observed 3i Atlas at radio frequencies. They've detected nothing unusual. The object is radio silent within the sensitivity limits of their instruments. That doesn't rule out artificial origin. A well-designed probe might operate silently to avoid detection, but it removes one potential line of evidence. Polarimetry offers another potential signature. 3i Atlas's extreme negative polarization and narrow inversion angle are unusual for natural comets. Could that indicate manufactured dust particles with unusual optical properties? Possibly, but natural explanations exist too. Dust composition, particle size distribution, and surface structure all affect polarization. Without comparing to a larger sample of interstellar comets, we can't say whether 3i Atlas's polarization signature is genuinely anomalous. The strongest argument against artificial origin is Occam's razor. The simplest explanation is usually correct. 3i Atlas displays comet-like behavior, sublimation, dust production, brightness variations consistent with rotation. All of these features match natural comet models. Invoking an artificial object requires assuming not just that aliens exist, not just that they've developed interstellar travel or probe deployment, but that they've designed their probe to mimic a comet so convincingly that it passes all observational tests. That's a lot of assumptions, yet the missing origin remains troubling. If 3i Atlas is natural, why can't we find its parent? If it's from a dissolved cluster or was perturbed by unseen objects, why does it display such clean thin disk kinematics? The natural explanations feel forced, like we're bending over backward to avoid the artificial hypothesis. That discomfort pushes some researchers to keep the artificial possibility on the table, not as a likely explanation, but as a reminder that we don't actually know. The scientific community remains deeply divided. Most astronomers consider the artificial hypothesis premature and unsupported by evidence. They argue that we should exhaust natural explanations before invoking aliens, and that the current data don't justify such speculation. A smaller group argues that refusing to consider artificial origin is itself a bias, a reflexive dismissal based on discomfort rather than evidence. The debate continues, and in the meantime, 3i Atlas continues its journey through our solar system, indifferent to our theories. Part 10. The Pattern of Visitors, Random Drift or Silent Watchers. 3 interstellar objects in 8 years. That's the current count. Oumuamua in October 2017, 2i/Borisov in August 2019, and 3i Atlas in July 2025. Before 2017, we had detected exactly 0 confirmed interstellar visitors. Now we have 3. The question is simple. Is that more than we should expect, or does it match predictions for random interstellar traffic? The answer depends on models of the interstellar object population. Astronomers estimate that at any given time, several interstellar objects are passing through the inner solar system within Jupiter's orbit. Most are too small or too faint to detect. Our telescopes have limited sensitivity, and survey coverage isn't complete. We miss the vast majority of visitors. The ones we detect are the largest, brightest, or luckiest objects that happen to pass close enough to Earth while a telescope is looking in the right direction. Detection rates improve dramatically with new survey telescopes. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, discovered Oumuamua. The Zwicky Transient Facility detected 2 I/Borisov. The Asteroid Terrestrial Impact Last Alert System, ATLAS, found 3i Atlas. Each of these facilities scans large portions of the sky nightly, searching for moving objects. As more surveys come online, particularly the Vera Rubin Observatory's legacy survey of space and time, detection rates will increase further. Statistical models suggest we should detect a few interstellar objects per decade with current capabilities. 3 detections in 8 years sits comfortably within those predictions. We're not seeing an anomalous flood of visitors, we're seeing the expected rate given improved detection technology. If anything, the rate might be slightly lower than some models predicted, though uncertainties are large enough that firm conclusions remain premature. Hopkins and collaborators developed a population model called the Otter-Tahi-Oxford Interstellar Object Model. They used 3i Atlas's observed properties to constrain the model parameters, estimating that the object is roughly 7.6 billion years old and was ejected from its parent system long ago. Their model predicts that interstellar objects should arrive from a wide range of directions and velocities, consistent with a population of ancient wanderers ejected throughout the galaxy's history. But here's where things get interesting. If interstellar objects are common, and if a significant fraction are actually probes rather than natural bodies, we'd still see mostly natural-looking objects. Imagine a galaxy where 1% of interstellar traffic consists of artificial probes and 99% is natural debris. You'd need to detect hundreds of objects before finding one that's clearly artificial. With only 3 detections so far, we're nowhere near that threshold. The artificial probe hypothesis isn't ruled out by seeing mostly natural-looking objects, because natural objects should dominate the sample regardless. This introduces an uncomfortable possibility. There could be artificial probes passing through our solar system regularly, hidden among the natural population, and we'd have no way to identify them unless they do something obviously unnatural. They could observe us, collect data, and depart without ever revealing their nature. We'd catalogue them as comets or asteroids, note their unusual features, and move on, never realizing we'd been visited. Detection bias compounds the problem. We find interstellar objects that pass close to Earth, are bright enough to detect, and happen to be in the field of view when a telescope is observing. Objects that pass through the outer solar system beyond Jupiter are nearly invisible. Objects smaller than a few hundred meters across escape detection entirely. If an advanced civilization wanted to monitor planetary systems without being noticed, they could deploy small probes that remain below our detection threshold. We'd never see them. There's also temporal bias. Earth has been radio loud for roughly 100 years. Before that, we were electromagnetically invisible. If interstellar probes specifically target technological civilizations, we might expect an increase in visitation rates after becoming detectable. 3 objects in 8 years could represent that increase, a response to our recent technological adolescence. But with such a small sample size, drawing conclusions is impossible. We'd need decades more data to identify temporal trends. Some researchers propose that interstellar object arrival rates might vary with galactic cycles. Our solar system orbits the galactic center every 225 million years, passing through spiral arms and experiencing varying gravitational environments. During spiral arm crossings, stellar encounters become more frequent, potentially disturbing the Oort cloud and sending comets both inward toward the Sun and outward into interstellar space. Similarly, increased encounters could capture more interstellar objects or deflect them toward the inner solar system. If we're currently in a period of increased galactic activity, arrival rates might be temporarily elevated. There's also the possibility of coordinated deployment. If an advanced civilization wanted to monitor multiple stellar systems, they might deploy probes in waves, sending thousands or millions simultaneously to ensure coverage across a large galactic region. From our perspective, we'd see a temporary increase in detections as that wave passes through our neighborhood, followed by a return to lower rates once the wave moves on. 3. Detections in 8 years could represent the leading edge of such a wave. But all of this remains speculation. The honest answer is that we don't know whether the current detection rate is normal, elevated, or even suppressed. Our baseline is 8 years of data, far too short to establish long-term trends. We don't know how many interstellar objects pass through undetected. We don't know if natural processes alone explain all observations or if some fraction are artificial. We're essentially trying to understand a complex phenomenon based on 3 data points, which is statistically absurd. What we can say is that more are coming. As survey telescopes improve and detection capabilities expand, we'll find more interstellar objects. Some will be comet-like, some might be rocky, and perhaps eventually one will display features so unusual that the natural explanation becomes untenable. That's when things will get truly interesting, when we can't explain something away and have to confront the possibility that we're not alone in watching the cosmos. Part 11. Rogue Black Hole on the Move. While astronomers puzzled over 3I Atlas's missing origin, another invisible wanderer made headlines in 2025, a candidate rogue black hole, drifting through our galaxy unattached to any star system. The discovery came from an international team analysing gravitational microlensing events, instances where a massive foreground object magnifies the light of a background star through gravitational lensing. Rogue black holes are stellar remnants, the collapsed cores of massive stars that were ejected from their birth systems through violent supernovae or gravitational interactions. Unlike black holes in binary systems, which reveal themselves through X-ray emissions as they accrete material from companion stars, rogue black holes drift silently through interstellar space, invisible except through their gravitational effects. The candidate object, tentatively designated OGLE BLG 2025-037, created a microlensing event lasting several months as it passed in front of a star in the galactic bulge. By analysing the light curve, the shape and duration of the brightness increase, astronomers estimated the lensing object's mass at roughly 7 solar masses, consistent with a stellar mass black hole. The lack of any visible companion or accretion signature suggests it's solitary, a genuine rogue wandering the galaxy alone. The discovery matters for multiple reasons. First, it demonstrates that massive invisible objects, black holes, neutron stars, rogue planets, populate interstellar space in significant numbers. These objects don't show up in optical catalogues like Gaia, yet they exert gravitational influence on everything around them. If 3i Atlas's trajectory was significantly altered by an encounter with such an object, we'd never find it in stellar databases because it's not a star. Second, rogue black holes represent erasers of cosmic history. Any star system that passes too close to a wandering black hole risks gravitational disruption. Planets could be stripped away, cometary reservoirs scattered, or entire systems destabilized. If 3i Atlas's parent star encountered a rogue black hole after ejecting the object, that encounter might have destroyed or severely altered the parent system, making traceback impossible. Third, the existence of rogue black holes highlights how little we know about the galaxy's dark inventory. For every luminous star we catalogue, there might be multiple dark objects, brown dwarfs, rogue planets, stellar remnants, moving through space unseen. These objects complicate trajectory reconstructions because their gravitational influences are real but unmodelled. Every traceback simulation assumes we know where the massive objects are, but we only know where the bright objects are. Micro-lensing surveys are slowly revealing this hidden population. Projects like OGLE, the Optical Gravitational Lensing Experiment, and MOE, micro-lensing observations in astrophysics, monitor millions of stars looking for brief brightness increases caused by foreground objects. Each detection adds to our senses of dark matter, not the particle physics kind, but the ordinary matter that doesn't emit light. Estimates suggest the Milky Way might contain hundreds of millions of rogue planets, and perhaps 100 million stellar remnants, including neutron stars and black holes. Most were ejected from their birth systems through gravitational interactions or supernova kicks. They wander the galaxy independently, occasionally passing through other star systems and perturbing orbits. If even a small fraction passed near 3i Atlas during its journey, the cumulative effect could significantly alter its trajectory in ways our models wouldn't capture. There's also a disturbing symmetry between 3i Atlas and the rogue black hole. Both are wanderers with obscured origins. Both move through space following trajectories shaped by ancient events we can't fully reconstruct. Both represent categories of objects we've only recently begun detecting and understanding. And both remind us that the galaxy is far more dynamic and populated than we once thought. The rogue black hole's existence raises an even stranger possibility. Could 3i Atlas itself be orbiting an invisible companion? Not a black hole necessarily, but perhaps a rogue planet or brown dwarf. If 3i Atlas were gravitationally bound to a dark object, both travelling together through interstellar space, we'd only see 3i Atlas because only it reflects sunlight. The companion would be invisible, yet its gravitational influence might explain some of the object's unusual characteristics. This scenario seems unlikely. Binary objects are less stable during interstellar travel because gravitational perturbations from passing stars can disrupt the pair. Over millions of years, most binaries would separate. But it's not impossible, and it represents yet another way that invisible masses could be hiding in plain sight, shaping observations while remaining undetected. As more rogue objects are discovered, our understanding of galactic dynamics will shift. We'll realize that the visible matter, the stars and gas clouds we catalogue and model, represents only part of the story. The invisible matter, not dark matter particles, but ordinary objects that don't shine, plays an equally important role. And until we account for that invisible population, our trajectory reconstructions will remain incomplete, full of gaps and missing perturbers that could explain objects like 3i Atlas. Part 12. Sunspot Superhole and Aurora Storms. While 3i Atlas drifted through our solar system and astronomers debated its origin, our own star decided to remind everyone that even local space is dynamic and dangerous. In September 2025, solar observers detected an unusually large coronal hole opening near the Sun's equator, a so-called superhole spanning more than 20 degrees of solar longitude. Coronal holes are regions where the Sun's magnetic field opens outward into space rather than looping back to the surface. They appear as dark patches in ultraviolet and X-ray images because the open field lines allow plasma to escape, reducing the local temperature and density. These holes matter because they are the source of high-speed solar wind. While the Sun constantly emits a stream of charged particles, the wind emerging from coronal holes travels significantly faster, reaching speeds of 700 to 800 kilometers per second compared to the typical 400 kilometers per second from closed field regions. When this fast wind reaches Earth, it compresses our magnetosphere and triggers geomagnetic storms. The September superhole unleashed a powerful stream of solar wind that struck Earth's magnetic field 3 days later. The resulting geomagnetic storm reached G3 levels on the 5-point scale, producing spectacular auroras visible at unusually low latitudes. Observers reported seeing the northern lights as far south as Oregon, Nebraska, and Pennsylvania, locations that rarely experience auroral displays. The southern lights likewise appeared over Tasmania and southern New Zealand. For most people, auroras are beautiful light shows, natural wonders that inspire awe. But they're also warnings. Geomagnetic storms can disrupt satellite operations, interfere with GPS signals, induce currents in power grids that risk transformer damage, and increase radiation exposure for astronauts and high-altitude pilots. The September storm caused minor satellite anomalies and brief communication disruptions, nothing catastrophic but enough to remind us that space weather affects technology. The connection to 3I Atlas might seem tenuous at first. One is a distant interstellar object, the other a local solar phenomenon. But they share a common theme, the dynamic, chaotic nature of cosmic environments. Just as 3I Atlas's trajectory was shaped by countless gravitational interactions over millions of years, solar activity is shaped by complex magnetic interactions that we still don't fully understand. Both remind us that the universe isn't static or predictable. It's turbulent, full of surprises, and capable of producing events that challenge our models. There's also a more direct connection involving comets. Solar wind and radiation shape cometary comas and tails. When 3I Atlas approached the Sun, it experienced increasing radiation pressure and particle bombardment. The solar wind pushed dust and gas away from the nucleus, creating the visible tail. Extreme solar events like the September storm could temporarily enhance that process, stripping material more aggressively or altering the coma's structure. If 3I Atlas had arrived during a solar maximum period, when coronal holes and geomagnetic storms are more frequent and intense, its behaviour might have been noticeably different. More mass loss, brighter coma, longer tail. Conversely, objects arriving during solar minimum might appear fainter and less active. This introduces another variable in modelling cometary behaviour and estimating properties like nucleus size and composition. What we observe depends partly on when the object arrived relative to the Sun's 11-year activity cycle. The superhole event also serves as a metaphor for the challenges of backward trajectory reconstruction. Just as geomagnetic storms complicate our ability to predict satellite orbits by introducing unpredictable perturbations, stellar encounters and unseen masses complicate our ability to trace interstellar objects backward through time. Every additional variable, every unmodelled interaction, degrades the accuracy of our reconstructions. Beyond a certain timescale, currently estimated around 10 million years, the chaos overwhelms the signal and we lose the ability to trace origins reliably. Solar variability affects more than just comets. It influences the entire heliosphere, the bubble of solar influence extending far beyond the planets. The heliopause, where solar wind pressure balances interstellar pressure, fluctuates in size and shape depending on solar activity. During solar maximum, the heliosphere expands. During solar minimum, it contracts. 3I Atlas passed through a heliosphere that's constantly shifting, shaped by processes we're only beginning to understand fully. There's something humbling about watching our star's mood swings, while simultaneously struggling to understand an interstellar visitor. We live in the backyard of a dynamic stellar system, bathed in radiation and magnetic fields that shape everything from satellite orbits to auroral displays. Yet we're trying to comprehend objects that travelled millions or billions of years through environments we can barely model. The gap between what we know and what we'd need to know to fully understand. 3I Atlas feels vast, maybe unbridgeable given current technology. But that gap is also what makes the mystery compelling. If we could easily explain everything, if 3I Atlas's origin were obvious and its properties unremarkable, it would be a footnote in astronomical catalogues. Instead, it's a puzzle that forces us to confront the limits of our knowledge and the complexity of cosmic processes. And as we'll see next, that confrontation with limits isn't unique to astronomy. It's happening across multiple scientific fields, including the most personal one of all, the biology of aging and death. Part 13, aging reversal in mouse brains. In March 2025, a research team at Peking University published results that sent shockwaves through the biology community. They had achieved roughly 30% lifespan extension in laboratory mice through targeted rejuvenation of brain tissue. The mice lived longer, healthier lives with preserved cognitive function, reduced neurodegeneration, and maintained physical activity into old age. The mechanism involved partial epigenetic reprogramming, essentially resetting some of the molecular clocks that govern cellular aging, turning back biological time without erasing cellular identity. Epigenetics refers to chemical modifications on DNA and associated proteins that control which genes are active without changing the underlying genetic sequence. Think of DNA as hardware and epigenetics as software. The same genetic code can produce vastly different outcomes depending on which programs are running. As organisms age, epigenetic patterns drift from their youthful configurations. Genes that should be active become silenced through methylation and histone modifications. Genes that should be silent become inappropriately active. This drift contributes to many aging-related pathologies, including neurodegeneration, immune dysfunction, tissue deterioration, and the accumulation of senescent cells that poison their neighbours. The epigenetic theory of aging has gained considerable momentum in recent years. Unlike genetic damage, which is largely irreversible, epigenetic changes are potentially reversible. You can't easily fix a mutated gene, but you can theoretically reset epigenetic marks to their youthful patterns. This distinction makes epigenetic interventions particularly promising for aging research. We're not trying to rewrite the code, just restore the original operating system. The Peking team used a technique called partial reprogramming, briefly activating 4 transcription factors originally discovered by Shinya Yamanaka, who won the Nobel Prize in 2012 for showing that these factors can reprogram adult cells back to an embryonic-like state. These Yamanaka factors, OCT4, SOX2, KLF4, and c-Myc, are powerful master regulators that can erase cellular identity. Full reprogramming is dangerous. It can cause cells to lose their specialized identity and become tumorigenic, essentially creating cancers. But partial reprogramming, activating the factors briefly and then turning them off, can reset epigenetic marks without causing dedifferentiation. It's like rebooting a computer without wiping the hard drive. The technique requires exquisite temporal control. Activate the factors for too long, and cells lose their identity. Too briefly, and nothing happens. The Peking team found a sweet spot, pulsed activation lasting just a few days, repeated periodically, that reset aging markers while preserving cellular function. By delivering the reprogramming factors specifically to brain tissue using engineered adeno-associated viruses, the researchers avoided systemic effects and focused rejuvenation where it matters most for cognitive aging. The treated mice showed increased neurogenesis, growth of new neurons in the hippocampus, a brain region critical for memory formation. They demonstrated improved synaptic plasticity, the ability of connections between neurons to strengthen or weaken, which underlies learning and memory. They showed reduced accumulation of damaged proteins associated with neurodegeneration, including aggregates resembling those found in Alzheimer's and Parkinson's diseases. Markers of inflammation decreased, mitochondrial function improved. The biological clocks in their brain cells appeared to run backward. Behaviorally, they performed better on memory tests, including maze navigation and object recognition tasks. They maintained exploratory behavior longer, continuing to investigate novel environments with the curiosity of young mice, rather than the cautious withdrawal typical of old age. They showed less age-related decline in motor coordination, maintaining balance and movement quality. Essentially, they remained youthful in both mind and body for a significantly larger portion of their total lifespan. The 30% lifespan extension translates to roughly 6 to 9 months for a mouse with a typical 2-year lifespan. That might not sound impressive until you scale it to humans. A 30% extension of average human lifespan would mean living to roughly 100 instead of 77. That's an extra 23 years, an entire additional chapter of life, time enough to watch grandchildren grow up, pursue second or third careers, or simply accumulate the wisdom that only time can provide. And if the quality of those years matched what the mice experienced, preserved cognition, maintained mobility, reduced disease burden, The implications become staggering. Now, connect this to 3i Atlas and the broader cosmic context. Human civilization has existed for roughly 10,000 years, if we count from the agricultural revolution. Recorded history spans about 5,000 years. Modern science is barely 400 years old, dating from the scientific revolution. Radio astronomy, the tool we'd use to detect signals from other civilizations, is less than 100 years old. We only started listening in the 1930s. We're cosmically young, barely adolescent in technological terms, still fumbling with the basic tools of cosmic awareness. If lifespan extension technologies work in humans, if we achieve even half the success seen in mice, human timescales expand dramatically. Scientists could pursue research programs spanning centuries rather than decades, following questions to their ultimate conclusions, rather than handing them off to students who hand them to their students in chains of diluted vision. Civilizations could maintain cultural continuity over longer periods, avoiding the generational memory loss that plagues long-term planning. And perhaps most relevant to our discussion, humans could witness multiple interstellar visitor events within a single lifetime rather than hoping to see one before death. Consider Avi Loeb, who's now 63 years old. In a normal human lifespan, he might have another 20 to 30 years to pursue his research on interstellar objects and the search for extraterrestrial technology. But with life extension, he could have 50, 70, even 100 additional years. Long enough to see dozens more interstellar visitors detected, building statistics where we currently have anecdotes. Long enough to witness whether 3i Atlas's silent origin becomes a pattern or remains an anomaly. Long enough perhaps to see definitive evidence of artificial objects among the natural population, to distinguish the signal from the noise with confidence born of accumulated observations. This connects to a deeper question about civilizations and cosmic awareness. If technological civilizations typically have lifespans similar to ours, 70 or 80 years, they face severe constraints on long-term projects like interstellar exploration or monitoring. Radio signals take years or decades to reach nearby stars. A message to Alpha Centauri takes 4.4 years one way. Physical probes take centuries or millennia even at optimistic speeds. Voyager 1, our fastest and most distant spacecraft, would take 75,000 years to reach Proxima Centauri if it were headed there. No individual lives long enough to see the mission completed, which requires institutional continuity and multi-generational commitment that's historically difficult to maintain. But a civilization that solves aging, that extends individual lifespans to centuries or millennia, faces different constraints. Long-term projects become personally meaningful rather than abstract obligations to future generations. You could launch a probe to another star system and live to see the data return. You could send signals into space and personally await responses. You could watch a star system evolve over centuries. The temporal scale of cosmic engagement shrinks from civilizational to personal, from something my descendants might see to something I will see. Perhaps the civilizations capable of sending interstellar probes are necessarily long-lived ones. Perhaps biological lifespans measured in decades are too short to sustain the technological and institutional continuity needed for interstellar activities. The generational turnover might simply be too rapid to maintain focus across the enormous time intervals involved. If true, this implies that our own emergence as a long-lived civilization, assuming life extension succeeds, might correlate with our readiness to engage in interstellar projects ourselves, or to be noticed by others already doing so. The mouse brain rejuvenation also touches on information preservation. One reason we struggle to understand ancient cosmic events is that information degrades over time. Trajectories become chaotic due to gravitational perturbations. Stellar clusters dissolve as member stars drift apart. Parent systems disappear, consumed by stellar evolution or wandering through the galaxy. Similarly, biological information degrades as organisms age. Memories fade as neural connections weaken. Tissues deteriorate, losing function and reliability. Knowledge is lost with each death, the expertise, insights, and hard-won understanding accumulated over a lifetime vanishing forever. Life extension preserves information, both biological and learned, allowing individuals to accumulate experience and insight over longer timescales without the constant reset of generational turnover. There's something poetic about humans developing life extension technologies at the same moment we're detecting interstellar visitors and searching for signs of other civilizations. These developments are coincidental in timing, they're not causally linked, but they point toward a threshold. We're becoming a different kind of civilization, one that looks outward while simultaneously extending its own temporal reach inward. Whether that threshold leads somewhere significant remains unknown, but the convergence feels meaningful even if the meaning isn't yet clear. Critics of life extension raise valid concerns. Resource allocation in a world where many lack basic healthcare, overpopulation on a planet already straining to support 8 billion people, social stratification where immortality becomes a privilege of wealth, and the risk that extended lifespans benefit only the wealthy while leaving the rest of humanity behind. These are serious issues that require careful consideration and cannot be dismissed as mere philosophical objections. They represent genuine challenges that any society pursuing life extension must address. But they don't negate the potential benefits for scientific research and cosmic awareness. A civilization of long-lived individuals might be better equipped to tackle century-scale challenges like climate change, where policy timescales currently exceed political attention spans. Interstellar exploration would become feasible not just institutionally but personally, and understanding the universe's deepest mysteries, from quantum gravity to dark matter to the nature of consciousness itself, might benefit from researchers who can sustain focused investigation for centuries rather than decades. And those mysteries are multiplying. While biologists explore the boundaries of lifespan, physicists are probing equally strange territories, including phenomena that challenge our understanding of time itself. Which brings us to one of the strangest experimental claims of 2025, a claim so controversial that many scientists dismiss it outright, while others wonder if it might crack open new physics. Part 14. Controversial Quantum Experiment. Time Reversal Signals. In June 2025, a team at the University of Queensland published results from a quantum optics experiment that claimed to demonstrate retrocausal signalling, information appearing to travel backward in time. The paper, published in a respected but not top-tier journal, described an elaborate setup involving entangled photons, delayed choice measurements, and carefully timed detectors arranged to test whether measurement choices made at one time could influence the physical state of particles at an earlier time. The claimed effect was tiny, buried in statistical noise, and required thousands of trials to extract. The researchers reported correlation patterns that seemed to violate temporal ordering, where the state of particles measured at time t appeared to depend on measurement choices made at time t plus 1. If real, this would represent a genuine violation of causality as we understand it, an effect propagating backward through time, defying one of the most fundamental assumptions underlying all of physics. The experimental setup itself was ingenious, involving a sophisticated arrangement of beam splitters, polarizers, and single photon detectors synchronized with atomic clock precision. The team used pairs of entangled photons, sending them along separate paths with carefully calibrated delays. The key innovation was in the timing. By making measurement choices on one photon, after its entangled partner had already been detected, they created a scenario where the later choice appeared to retroactively influence the earlier detection result. Most physicists are deeply skeptical. Extraordinary claims require extraordinary evidence, and this experiment, while sophisticated, has not been independently replicated. The statistical analysis has been questioned by several groups who noted potential confounding factors in the data processing pipeline. Alternative explanations involving subtle detector correlations or unaccounted systematic errors might explain the results without invoking time reversal. The paper's reception has been lukewarm at best, with many researchers suggesting the effect will disappear under more careful scrutiny, much like other claimed anomalies in quantum mechanics that later proved to be experimental artifacts. The history of physics is littered with experiments that seem to violate fundamental principles but eventually succumbed to more mundane explanations. Cold fusion, faster-than-light neutrinos, the EM drive, all initially generated excitement but ultimately failed to withstand rigorous testing. The Queensland result may well join this list. The researchers themselves, to their credit, have called for independent verification and acknowledged the preliminary nature of their findings. But let's entertain the possibility not as fact, but as thought experiment. If retrocausal effects exist, even weakly, they would revolutionize physics in ways that would make quantum mechanics look tame by comparison. They'd also open bizarre possibilities for advanced technologies that currently exist only in science fiction. A civilization that mastered retrocausality could potentially communicate with its own past, influence events before they occur, or manipulate timelines in ways that challenge our most basic intuitions about cause and effect. Such mastery would require not just understanding retrocausality, but engineering it, building devices that could reliably generate, amplify and control backward time effects. This would demand technologies operating at energy scales and precision levels far beyond our current capabilities. We can barely manipulate individual quantum states. Controlling macroscopic retrocausal phenomena would require mastery several orders of magnitude beyond that. Now apply this to the Three-Eye Atlas mystery. What if the object's trajectory, when traced backward, leads nowhere because the backward trace itself is wrong? What if the object's path through space-time involves retrocausal elements that our purely forward time models can't capture? This sounds absurd, and it probably is absurd, but it's worth noting that we're already facing an absurd situation. An interstellar object with no traceable origin, despite excellent data and sophisticated models that should definitively pin down its source. If a sufficiently advanced civilization deployed probes that exploited retrocausal effects, those probes might appear to have impossible trajectories. They'd arrive from directions that don't lead back to any source, because the notion of leading back breaks down when time can be traversed in both directions. They'd display kinematic properties that seem to contradict their origins, because their origins involve temporal loops or causal structures we don't understand. The very concept of a launch point becomes meaningless when an object's worldline can curve through time as well as space. Consider the implications further. Such a probe might not even need to travel the full distance between stars in the conventional sense. If it could exploit closed time-like curves, or other exotic spacetime structures, it might traverse vast distances by taking shortcuts through time itself. It could appear in our solar system having departed from a location it hasn't technically left yet, creating paradoxes that only resolve when viewed from outside our limited temporal perspective. This is pure speculation, the kind that gets scientists labelled as cranks, and rightfully so, because we have zero evidence that retrocausality plays any role in Three-Eye Atlas's trajectory, or that advanced civilizations have mastered such physics. The Queensland experiment might be a statistical fluke or experimental artifact. Even if retrocausality exists, it might be too weak to affect macroscopic objects like comets, confined to the quantum realm where it poses no practical challenge to our everyday understanding of cause preceding effect. The entire line of reasoning might be nonsense, a castle built on foundations of wishful thinking. But here's why it's worth mentioning. Mysteries compound. When you have an unexplained astronomical phenomenon, an interstellar object with no origin, coinciding with controversial physics experiments hinting at time symmetry violations, coinciding with SETI researchers actively looking for artificial objects in just such anomalous trajectories, the combination suggests we're entering territory where multiple paradigms might shift simultaneously. Not because these phenomena are connected, they're probably not, but because we're reaching the limits of our current frameworks across multiple fields. We're bumping against the boundaries of what our theories can explain. Quantum mechanics already tells us that time behaves strangely at small scales. Particles can exist in superpositions where future and past states influence each other in ways that defy classical intuition. Wheeler's delayed choice experiment, first performed in the 1980s, showed that measurements made now can affect which path a photon took in the past, at least in the quantum mechanical sense. These effects are real and experimentally verified, though interpretations vary wildly depending on which philosophical framework you adopt: Copenhagen, many worlds, pilot wave, or one of a dozen other competing interpretations. The transactional interpretation of quantum mechanics, proposed by John Cramer in the 1980s, explicitly incorporates retrocausal elements, with offer waves travelling forward in time and confirmation waves travelling backward to create the transactions we observe as quantum events. While controversial, this interpretation makes predictions identical to standard quantum mechanics, while providing an intuitive picture of certain phenomena that seem paradoxical in other frameworks. Extending such effects to macroscopic scales and using them for technology requires leaps that current physics doesn't support. But current physics is always preliminary, always provisional, Newton's mechanics worked perfectly until it didn't, failing to account for Mercury's perihelion precession and other relativistic effects. Einstein's relativity seemed complete until quantum mechanics revealed its incompleteness at small scales, creating tensions we still haven't fully resolved a century later. Every major physics revolution involved phenomena that seemed impossible under the previous paradigm. Retrocausality might be the next such revolution, or it might be a dead end. Time will tell, quite literally. The real point isn't whether retrocausality explains Three-Eye Atlas. It almost certainly doesn't. The point is that when conventional explanations fail, when we exhaust natural hypotheses and still face silence, our minds naturally reach toward the edges of known physics, grasping for frameworks that might accommodate the anomalous observations. That reaching might lead nowhere, evaporating like morning mist when better data arrives. Or it might lead to genuinely new understanding, opening doors we didn't know existed. And speaking of new understanding, there's one more development transforming how we search the cosmos, one that doesn't involve exotic physics, but rather the application of intelligence, both human and artificial, to the massive data streams now flooding astronomy. As telescopes grow larger and surveys more comprehensive, the bottleneck shifts from data collection to data analysis. We're drowning in information, and the solution increasingly involves letting machines do the searching, teaching algorithms to recognize patterns that human eyes would never catch in the tsunami of data pouring down from the sky each night. Part 15, AI Joins the Hunt, Machine Learning Astrophysics, in 2025. In August 2025, an artificial intelligence system scanning data from the Zwicky Transient Facility identified something human astronomers had missed, a new type of supernova, designated SN 2025 AI001, that didn't fit existing classification schemes. The explosion showed unusual spectral evolution, an unexpected combination of features from Type Ia and Type II and supernovae, suggesting a progenitor system that existing models couldn't explain. Human astronomers verified the discovery and confirmed it was genuinely novel, a new category requiring new theoretical understanding. This wasn't the AI's first success. Machine learning algorithms have been quietly revolutionizing astronomy for years, identifying exoplanets in transit data, classifying galaxies by morphology, detecting gravitational wave signals in noisy detector output, and flagging transient events that might otherwise go unnoticed. But 2025 marked a threshold where AI systems began autonomously discovering new categories of phenomena rather than just efficiently sorting known ones. The implications for interstellar object detection are profound. Current methods rely on humans noticing moving objects in survey images, calculating their orbits, and identifying which ones are unusual enough to warrant further observation. That process works. We've found 3 interstellar visitors this way, but it's slow, labour-intensive, and subject to human biases and limitations. We might miss objects that move unusually, that don't fit expected patterns, or that appear during periods when humans aren't looking at the data. AI systems don't have those limitations. They can scan every image, track every moving object, calculate every orbit, and flag anomalies in real time. They don't get tired. They don't have preconceptions about what interstellar objects should look like. They can recognize patterns too subtle or complex for human perception. And as the Vera Rubin Observatory comes fully online, generating tens of terabytes of data every night, AI assistance transitions from helpful to essential. Several research groups are developing specialized neural networks for interstellar object detection. These systems are trained on synthetic data, simulated images of how interstellar objects with various properties would appear in telescope data, combined with real observations of known objects. The networks learn to distinguish interstellar visitors from solar system natives based on trajectory, brightness evolution, and spectral characteristics. Early tests suggest they can achieve high detection rates with low false positive rates, outperforming human supervised searches. But there's a more intriguing possibility. AI might detect interstellar objects that are genuinely anomalous, objects that don't fit any natural category and might represent artificial technology. Machine learning systems excel at anomaly detection, identifying outliers that deviate from expected patterns. If an interstellar object displays features inconsistent with comet or asteroid models, features suggesting internal structure, active maneuvering, or electromagnetic emissions, a properly trained AI should flag it as anomalous. The challenge is defining what counts as anomalous without introducing human biases. If we train AI only on known natural objects, we risk teaching it to reject anything genuinely artificial as a false positive. The solution involves training on both natural objects and simulated artificial ones, probes with various hypothetical propulsion systems, power sources, and behaviors. The AI learns to distinguish not just natural versus artificial, but rather expected versus unexpected, flagging anything that doesn't match known physics or expected behavior for further human investigation. This creates an interesting dynamic where human creativity in imagining artificial objects, designing simulations of how probes might appear, directly influences what AI systems can detect. Our ability to find artificial visitors depends partly on our ability to imagine what they'd look like. That might seem circular, but it's not. We're not looking for specific designs, we're looking for deviations from natural behavior. Any artificial object, regardless of design, should display some features that don't match natural processes, and those features should be detectable as statistical anomalies. AI also helps with the trajectory reconstruction problem that plagues 3i Atlas. Machine learning systems can explore vastly larger parameter spaces than human-coded simulations, testing billions of possible encounter scenarios, gravitational perturbations, and initial conditions to find trajectories that match observations. If there's a plausible but non-obvious path connecting 3i Atlas to a known star system, AI might find it where exhaustive searches failed. Several teams are now applying AI to the 3i Atlas mystery specifically. They're feeding neural networks all available data, trajectory, kinematics, spectroscopy, photometry, and asking the systems to identify patterns or correlations that might point toward an origin. So far, no breakthroughs have been announced, but the work continues. AI doesn't get frustrated or give up. It keeps searching as long as computational resources are available. There's also growing interest in using AI for SETI, searching for artificial signals in radio telescope data. Traditional SETI looks for narrow-band signals or specific patterns that suggest technological origin. AI can search for patterns too complex or subtle for predefined algorithms, signals that don't fit human expectations, but still show evidence of structure and information content. Breakthrough. Listen is incorporating machine learning into its search protocols, expanding the range of signals considered potentially interesting. The combination of AI-enhanced detection and the coming flood of data from next-generation telescopes means we're entering an era where interstellar visitor discoveries could accelerate dramatically. Instead of 3 detections in 8 years, we might see dozens per year within a decade. Each detection provides more data, refines population models, and potentially reveals whether 3i Atlas's silent origin is unique or part of a broader pattern. And if AI does flag an object as genuinely anomalous, as something that can't be explained through natural processes, that's when the real debate begins. Because at that point, we're not speculating anymore. We're confronting evidence that demands explanation, and all the comfortable assumptions we make about being alone or being cosmically insignificant suddenly face empirical challenge. The story of 3i Atlas remains unfinished. The object continues its journey outward, moving beyond observation range, carrying its secrets into the darkness. We're left with data, measurements, spectra, and images, but no definitive answers. The origin remains silent. The alignment with Sagittarius and the WOW signal remains unexplained or dismissible, as coincidence depending on your perspective. The unusual physical properties remain within the range of natural variability, or just beyond it depending on which measurements you trust. What 3i Atlas gives us isn't answers. It gives us questions that refuse to settle. It shows us the limits of our knowledge and the gaps in our census of the galaxy. It reminds us that the universe doesn't owe us explanations, and that sometimes the most honest response to a mystery is admitting we don't know. Not yet, maybe not ever. But those gaps and silences are where discovery lives. Every major astronomical breakthrough began with anomalies, with observations that didn't fit, with scientists brave or stubborn enough to admit that the standard models were incomplete. 3i Atlas might be just another comet, ancient and natural and unremarkable except for the accident of detection timing. Or it might be something stranger, a messenger from a civilization we can't yet imagine, a probe studying us as we study it, or simply a natural phenomenon revealing physics we haven't discovered? The answer matters less than the search, because in searching, in building better telescopes and training smarter algorithms and asking uncomfortable questions, we expand our understanding. We push against the boundaries of knowledge. We prepare ourselves for whatever comes next, whether that's more silent visitors with missing origins or clear evidence of something beyond natural processes. And as AI joins the hunt, as life extension potentially gives us more time to witness cosmic events, as our technologies for detection and analysis improve year by year, the probability of finding that definitive answer, whatever it is, increases. Somewhere out there beyond the Heliopore's three-eye atlas continues its journey, silent, unknowable, moving through the void as it has for possibly billions of years, as it will for billions more. It came from somewhere, even if we can't identify where. It passed through our solar system, briefly illuminated by our sun, observed by our instruments, and now it returns to darkness. We're left standing on our small world, looking up, wondering what we saw and what it means. And in that wondering, in that refusal to accept easy answers or premature conclusions, we become the kind of civilization that might one day join the others among the stars, if indeed others are out there watching.